Imagine you're moving to a new apartment and need to pack 23 books into boxes. Each box holds exactly 10 books. How many boxes do you need? You might think 2.3 boxes, but you can't buy part of a box. You need exactly 3 complete boxes. This is where the ceiling function becomes incredibly useful. This rounding up behavior is exactly what the ceiling function does. The ceiling function is a mathematical tool that takes any real number and gives you the smallest integer that is greater than or equal to that number. The ceiling function uses special notation. We write it as x surrounded by these ceiling brackets, or we can write ceil of x. Both mean exactly the same thing. Now let me show you exactly how this works with some clear examples. We'll start with positive numbers, then look at negative numbers, and finally see what happens with whole numbers. First example, what is the ceiling of 2.3? We need the smallest integer greater than or equal to 2.3. Looking at our number line, 2.3 sits between 2 and 3. Since we need an integer greater than or equal to 2.3, we jump up to 3. Now for a negative example, what is the ceiling of negative 2.3? This is where students often make mistakes. We still need the smallest integer greater than or equal to negative 2.3. On the number line, negative 2.3 sits between negative 3 and negative 2. The smallest integer greater than or equal to negative 2.3 is negative 2, not negative 3. Finally, what happens with whole numbers? The ceiling of 5 is simply 5. When the input is already an integer, the ceiling function returns that same integer, because 5 is already the smallest integer greater than or equal to itself. So remember, the ceiling function always rounds up to the next integer, except when the number is already a whole number. This makes it perfect for situations where you need complete units, like our box example at the beginning. In the next sections, we'll explore the mathematical notation in more detail and see many more examples. Now that we understand what the ceiling function does, we need to learn how mathematicians write it and express it formally. There are 2 main ways to represent the ceiling function, and understanding both is crucial for your mathematical studies. The primary mathematical notation for the ceiling function uses special brackets that look like the upper half of square brackets. We write it as ceiling of x, where x is enclosed between these ceiling symbols. Notice these special bracket symbols. The left symbol opens upward, and the right symbol also opens upward. These are specifically called ceiling brackets, and they're different from regular square brackets or parentheses. In programming languages and spreadsheet software like Excel, we can't easily type those special ceiling brackets. So instead, we use the function notation, ceil of x, written as cell with parentheses. Both notations mean exactly the same thing. Whether you see ceiling of x with the special brackets or ceil of x with parentheses, they represent the identical mathematical operation. Now let's look at the formal mathematical definition. This might seem intimidating at first, but we'll break it down step by step to make it completely clear. The formal definition states, f of x equals the minimum of the set containing all integers a, such that a is greater than or equal to x. This looks complex, but each part has a specific meaning. The symbol z with the double line represents the set of all integers, negative numbers, 0, and positive numbers. The condition a is greater than or equal to x means we're looking at all integers that are at least as large as our input value x. Finally, minimum means we take the smallest value from this set of integers. So the ceiling function finds the smallest integer that is greater than or equal to x. In simple English, this formula says, to find the ceiling of x, look at all the integers that are greater than or equal to x, then pick the smallest one. That's exactly what we mean by rounding up to the nearest integer. So whether you see ceiling of x written with the special brackets, or ceil of x in programming notation, or the formal mathematical definition, they all represent the same concept, finding the smallest integer greater than or equal to your input value. Now that we understand how to write and read the ceiling function notation, we're ready to see it in action with specific examples. Now that we understand what the ceiling function is, let's work through several examples to see exactly how it behaves with different types of numbers. Our first example is ceiling of 2.4. Let's see where 2.4 falls on the number line and determine the smallest integer greater than or equal to it. Here's 2.4 on our number line. Notice that 2.4 falls between 2 and 3. Since the ceiling function gives us the smallest integer greater than or equal to our input, we need to round up to 3. Therefore, ceiling of 2.4 equals 3. The answer is 3 because 3 is the smallest integer that is greater than or equal to 2.4. Now let's try a negative number, which often confuses students. What is ceiling of negative 2.4? Remember, we still need the smallest integer greater than or equal to our input. Here's negative 2.4 on our number line. It falls between negative 3 and negative 2. Now, which integer is greater, negative 3 or negative 2? Remember that negative 2 is greater than negative 3, so ceiling of negative 2.4 equals negative 2. Even though we're dealing with negative numbers, we still round toward the greater integer, which is negative 2. What happens when we apply the ceiling function to an integer? Let's find ceiling of 5. Since 5 is already an integer, what do you think the result will be? Since 5 is already an integer, and we need the smallest integer greater than or equal to 5, the answer is simply 5 itself. When the input is already an integer, the ceiling function returns that same integer. Here's an interesting case, ceiling of 0.001. Even though 0.001 is very close to 0, what integer must we round up to? Even though 0.01 is extremely small, it's still greater than 0. The smallest integer greater than or equal to 0.001 is 1. This shows that the ceiling function always rounds up, no matter how close to an integer the input might be. Let's do one more negative example to make sure we understand this concept. What is ceiling of negative 1.7? Negative 1.7 falls between negative 2 and negative 1. Since negative 1 is greater than negative 2, we round up to negative 1. Remember, with negative numbers, rounding up means moving towards 0. These examples demonstrate the key behavior of the ceiling function. It always rounds up to the next integer, even for negative numbers where up means towards 0. When the input is already an integer, it stays the same. Now that we understand how the ceiling function works with individual numbers, it's time to visualize this function graphically. The graph of the ceiling function has a very distinctive and memorable appearance. The ceiling function graph looks exactly like a staircase. Each step represents a horizontal line segment that spans 1 unit in the x direction, and there are sudden jumps at every integer value. Let me build this graph step by step. For any x value between negative 3 and negative 2, the ceiling function equals negative 2. This creates our first horizontal segment. At x equals negative 2, we have a jump discontinuity. The function jumps from negative 2 up to negative 1. For x values between negative 2 and negative 1, the ceiling function equals negative 1. This pattern continues. At each integer value, we see a jump discontinuity, and between integers, we have horizontal line segments. Let me complete the rest of the graph. Now that we can see the complete graph, let's examine the key properties of the ceiling function. First, let's talk about the domain, the set of all possible input values. The domain of the ceiling function is all real numbers. This means we can input any real number, positive, negative, or 0, into the ceiling function. There are no restrictions on the input values. However, the range, the set of all possible output values, is much more restricted. The ceiling function can only output integer values. The most important property of the ceiling function graph is that it has discontinuities at every integer value. A discontinuity means there's a sudden jump in the function value. It's not smooth or connected at those points. Let me demonstrate this with a specific example. Consider what happens at x equals 0. As we approach 0 from the left, the function value is 0. But at x equals 0 itself, the function jumps up to 1. This discontinuous behavior is what gives the ceiling function its characteristic staircase appearance. Each horizontal segment represents a constant output value over an interval, and the vertical jumps occur precisely at integer input values. To summarize the key properties, the ceiling function has a domain of all real numbers, a range of all integers, and is discontinuous at every integer value. Its graph forms a distinctive staircase pattern that makes it easy to identify and work with visually. Now that we understand the ceiling function, we need to explore its close mathematical relative, the floor function. Understanding the difference between these two functions is crucial for avoiding common mistakes in mathematics. The floor function, denoted with square brackets pointing downward, returns the greatest integer less than or equal to x. Think of it as rounding down to the nearest integer. The key difference is direction. The ceiling function always rounds up, while the floor function always rounds down. Let me show you this with a visual comparison. Let me demonstrate this with some quick examples. For 2.7, the ceiling function gives us 3 because we round up, while the floor function gives us 2 because we round down. Let's work through our first example, comparing both functions with positive decimal numbers. We'll evaluate both the ceiling and floor functions for 3.2, 5.8, and 7.0. For 3.2, the ceiling function rounds up to 4, while the floor function rounds down to 3. Notice how they give different results for non-integer values. For 5.8, the ceiling function rounds up to 6, and the floor function rounds down to 5. The pattern is consistent for all positive decimals. Here's an important special case. For 7.0, both functions return 7 because 7 is already an integer. When x is an integer, both ceiling and floor functions return x itself. Example 2 involves negative numbers, which often confuse students. Remember, ceiling always rounds toward positive infinity, and floor always rounds toward negative infinity. For negative 2.3, the ceiling function gives us negative 2, which is the smaller integer closer to 0. The floor function gives us negative 3, which is further from 0. For negative 4.7, ceiling gives us negative 4, and floor gives us negative 5. This pattern holds for all negative non-integers. Again, for negative 6.00, both functions return negative 6 because it's already an integer. The rule about integers applies to negative numbers too. Our final example explores the mathematical relationship between ceiling and floor functions. There's a beautiful formula that connects them. Ceiling of x equals negative floor of negative x. Let's verify this formula using x equals 3.4. First, we'll calculate the ceiling of 3.4 directly, which gives us 4. Now let's use the formula. We need to calculate negative floor of negative 3.4. First, negative 3.4 equals negative 3.4. Next, the floor of negative 3.4 equals negative 4, because floor rounds down toward negative infinity. Finally, negative floor of negative 3.4 equals negative times negative 4, which equals positive 4. This matches our direct calculation. This relationship is extremely useful in advanced mathematics and computer science. It shows the deep connection between these two fundamental functions and provides an alternative way to calculate ceiling functions when only floor functions are available. The ceiling function isn't just a mathematical concept. It has numerous practical applications in everyday life and professional fields. From calculating postage costs to programming screen layouts, the ceiling function helps us solve real problems that require rounding up to the next whole number. Our first example involves calculating postage stamps. Imagine you need to mail a package that weighs 3.7 ounces, and each stamp covers 1 ounce of weight. How many stamps do you need? We need to divide the package weight by the weight each stamp covers. 3.7 divided by 1 equals 3.7. But we can't buy a fraction of a stamp, so we need to round up to the next whole number. This is where the ceiling function comes in. The ceiling of 3.7 equals 4, which means we need exactly 4 stamps to mail our package. Notice that even though we only need 3.7 stamps mathematically, we must purchase 4 complete stamps. The ceiling function ensures we have enough postage to mail our package. Our second example involves billing calculations. A consulting company charges clients in 15-minute increments. If a consultation lasts 47 minutes, how many billing increments should be charged? We divide the consultation time by the billing increment. 47 divided by 15 equals approximately 3.13. Since we can't charge a partial increment, we round up using the ceiling function. The ceiling of 3.13 equals 4 increments. This means the company will charge for 4 15-minute periods, totaling 60 minutes of billing time, even though the actual consultation was only 47 minutes. Our final example comes from computer programming. A developer needs to arrange 23 items in rows on a screen, with each row displaying exactly 6 items. How many rows are needed to display all items? We divide the total number of items by the number of items per row. 23 divided by 6 equals approximately 3.83. Since we need complete rows to display all items, we use the ceiling function. The ceiling of 3.83 equals 4 rows. This ensures all 23 items can be displayed, even though the last row will only contain 5 items instead of the full 6. These 3 examples demonstrate how the ceiling function solves practical problems across different fields. Whether calculating postage, billing clients, or programming layouts, the ceiling function ensures we always have enough resources by rounding up to the next whole number. Excel provides several ceiling functions that extend the mathematical ceiling concept into practical spreadsheet calculations. These functions are essential tools for financial modeling, data analysis, and business calculations. The basic ceiling function in Excel uses the syntax ceiling open parentheses number, comma, significance, close parentheses. The number parameter is the value you want to round up, and significance is the multiple to which you want to round. Now let's work through 3 examples to understand how Excel's ceiling functions work in practice, starting with the most basic usage. For our first example, we'll calculate ceiling of 3.2 with a significance of 1. First, let's identify our parameters. The number is 3.2 and the significance is 1. Step 2, we need to find the smallest multiple of 1 that is greater than or equal to 3.2. The multiples of 1 are 2, 4, and so on. Since 3 is less than 3.2, we need the next multiple, which is 4. Therefore, ceiling of 3.2 with significance 1 equals 4. This rounds 3.2 up to the nearest integer. Now let's explore a more complex example using a different significance value to see how this parameter affects the result. For our second example, we'll work with 2 different problems to show how significance affects the result. First, ceiling of 3.2 with significance 0.5, and second, ceiling of 7.3 with significance 2. For ceiling of 3.2 with significance 0.5, we find multiples of 0.5, 3.0, 3.5, 4.0. Since 3.0 is less than 3.2, but 3.5 is greater than 3.2, the result is 3.5. For ceiling of 7.3 with significance 2, we find multiples of 6, 8, 10. Since 6 is less than 7.3, but 8 is greater than 7.3, the result is 8. The key insight here is that significance determines the step size for rounding. Smaller significance values give more precise results, while larger significance values round to bigger intervals. Now let's explore Excel's advanced ceiling functions, ceiling.precise and ceiling math, which provide more control over rounding behavior, especially with negative numbers. Excel provides 3 ceiling functions. The basic ceiling function we've been using, ceiling.precise for more precise control, and ceiling.math, which includes an additional mode parameter for even more flexibility. The key difference between these functions becomes apparent with negative numbers. Let's test with negative 2.3 and significance 1 to see how each function behaves. For negative 2.3 with significance 1, ceiling returns negative 2. Ceiling.precise also returns negative 2. Ceiling.math with mode 0 returns negative 2, but ceiling.math with mode 1 returns negative 3, showing different rounding behaviors. Important note about error handling. If either the number or significance argument is non-numeric, all ceiling functions will return a value error. Always ensure your inputs are valid numbers. To summarize the key takeaways, ceiling provides basic rounding up functionality. Ceiling.precise offers more consistent behavior with negative numbers. Ceiling.math adds a mode parameter for maximum flexibility, and all functions handle the significance parameter in the same fundamental way. We've learned about the mathematical ceiling function, but there's an important statistical concept that shares its name, the ceiling effect. This is a critical pitfall that researchers and data analysts must understand to avoid drawing incorrect conclusions from their data. The ceiling effect is a statistical phenomenon that occurs when a measurement instrument cannot adequately capture the full range of a variable because too many participants score at or near the maximum possible value. This effect has several key characteristics that make it problematic for researchers. The measurement tool has a limited upper range. Many subjects cluster at the highest scores, and this clustering reduces our ability to detect meaningful differences between groups or conditions. Our first example demonstrates a simple ceiling effect scenario. A teacher administers a math test to 30 students with a maximum possible score of 100 points. When we examine the distribution of test scores, we see a clear ceiling effect. Most students, 20 out of 30, scored between 80 and 100 points, clustering at the high end of the scale. This means 67% of students scored in the highest range. This clustering makes it impossible to distinguish between students who might have scored 105, 110, or even higher if the test allowed it. The problem is clear. We cannot distinguish between high-performing students. The solution would be to use a more challenging test with a higher ceiling, allowing for better differentiation among top performers. Our second example involves a customer satisfaction survey that uses a 1 to 5 rating scale, where 1 means very dissatisfied and 5 means very satisfied. When we analyze the survey responses from 100 customers, we see a clear ceiling effect. 35 customers rated their satisfaction as 4, and 40 customers gave the highest rating of 5. This means 75% of all responses fall into the two highest categories. This ceiling effect prevents us from understanding the true range of customer satisfaction. Some customers might be extremely satisfied beyond the scale's maximum. The analysis reveals limited ability to measure exceptional satisfaction levels. Solutions include expanding the scale to 1 through 10 or adding open-ended questions to capture nuanced feedback. Our final example involves a psychology research study that measures reaction times using equipment with a technical limitation. It can only record reaction times up to 2.0 seconds. The measurement timeline shows that while the equipment can accurately record reaction times from 0 to 2 seconds, anything beyond 2 seconds cannot be measured, creating a ceiling effect. Looking at sample data from 50 participants, we see that 5 participants maxed out the equipment at 2 seconds. Their true reaction times could be 2.5 seconds, 3 seconds, or even longer. We simply cannot know. The statistical impact is significant. We cannot calculate the true mean reaction time because we're missing data from participants who exceeded the measurement ceiling. This also affects correlation and regression analyses, potentially leading to incorrect conclusions about reaction time patterns. To avoid ceiling effects in your research and data analysis, remember these key takeaways. First, recognize when measurements cluster at maximum values. Second, choose appropriate measurement scales with adequate ranges. Third, consider pilot testing to identify potential ceiling effects before full data collection. Fourth, use alternative measurement methods when ceiling effects are detected. And fifth, always report ceiling effects in your statistical analyses. Remember, ceiling effects can invalidate statistical conclusions and hide important differences in your data. Understanding both the mathematical ceiling function and the statistical ceiling effect gives you powerful tools for accurate data analysis and interpretation. By recognizing these patterns, you can make better decisions about measurement design and avoid common pitfalls in statistical research.